Two galaxies are on an inevitable collision course right now. This is the violent reality of galactic collisions, a chaotic process that forges new worlds from the wreckage of the old. By the end of this journey, you will understand how the universe uses these cosmic crashes not for destruction, but as a creative engine. We will uncover how entire solar systems can be born from the turmoil, and what happens when supermassive black holes are forced to dance. How does chaos on such an unimaginable scale lead to the birth of new planets? The Milky Way is so vast that a single beam of light takes over 100,000 years to cross from one edge to the other. Within that incomprehensible span, our galaxy holds between 100 billion and 400 billion stars. When another galaxy of similar scale drifts into its gravitational embrace, they do not meet with a cataclysmic bang. The event is far more subtle and far more drawn out. The average distance between stars is so immense that they slide past one another like distant ships on an empty ocean. A direct collision between two suns is almost unthinkably rare. The real force of the impact is not in stellar fire, but in an invisible, relentless pull. The gravitational fields of the two galaxies reach out and begin a slow, cosmic dance. They do not smash, they intertwine. Over hundreds of millions of years, these titanic forces pull and twist the majestic spiral arms, warping the very architecture of each galaxy into strange new shapes. This gravitational tug of war sets the stage for the profound transformation that follows, a chaotic process where the old order is dismantled to make way for the new. Even from millions of light-years apart, the galaxies feel the first gentle tug. This is the opening act of the collision, a slow-motion approach governed by gravity's invisible hand. As the galaxies spiral closer, that uniform pull becomes uneven. The force of gravity is stronger on the side of the galaxy facing its partner and weaker on the far side. This difference, a tidal force, begins to stretch each galaxy in a profound and beautiful way. It is the same principle that causes ocean tides on Earth, but operating on a truly galactic scale. The galaxies do not remain their pristine, spiral selves. They are pulled and deformed, with immense streams of gas, dust, and stars drawn out into the void. These are the tidal tails, luminous rivers of cosmic material flowing into intergalactic space. Far from being mere wreckage, these tails are the first nurseries. Within these chaotic streams, pockets of gas collapse under their own gravity, igniting into brilliant new star clusters. This gravitational stretching is the universe stirring a pot that has been still for eons, mixing ancient ingredients and setting the stage for a burst of new life. Yet the stars and glowing gas we see are merely the actors on a stage built by something far more mysterious. The true architects of this cosmic event are the vast, invisible halos of dark matter that surround each galaxy. This substance is not like anything we know. It does not emit, absorb, or reflect any form of light, making it completely undetectable to our telescopes. We only know it exists because of the powerful grip its gravity has on everything we can see. In fact, dark matter makes up about 85% of all the matter in the universe. It forms an immense, unseen scaffold that holds each galaxy together and dictates how they will interact. When two galaxies begin their long dance, it is not their visible stars that lead the way. Their dark matter halos are the first to meet. In computer simulations of these events, we see the ghostly halos pass right through one another, their strange nature preventing a direct collision. But their gravitational pull is immense, and this is what truly orchestrates the chaos. the invisible dark matter tugs and pulls on the stars and gas, dragging the visible components of the galaxies along for the ride. It is the unseen director of the entire ballet, choreographing the motions that will ultimately tear the old structures apart and forge new ones from the wreckage. This gravitational stretching is just the prelude. The first close encounter between the galactic cores is where the true chaos begins. The central bulges of the galaxies, packed with ancient stars, swing past one another at speeds of hundreds of kilometers per second. This is not a slow merging but a violent gravitational slingshot. Stars are whipped around, their orbits scrambled beyond recognition. Some are flung onto new, erratic paths within the newly combined system. Others are not so lucky. The immense gravitational forces can hurl them completely out of the galaxy, casting them adrift into the cold, dark emptiness of intergalactic space. These become rogue stars, solitary suns on an endless journey through the void, their planetary families, if they had any, dragged along into permanent exile. But while the stars are being scattered, the true builders are getting to work. The immense clouds of gas and dust that fill the galactic disks cannot simply slide past each other like stars. They slam together. When these colossal clouds collide, they create powerful shock waves that race through the material, compressing it to incredible densities. This sudden, violent pressure is the trigger for a firestorm of creation. Countless pockets of gas collapse under their own weight, heating up until nuclear fusion ignites in their cores. This is the first great wave of starbirth, lighting up the merging galaxies with the brilliant blue light of millions of newborn stars. The galactic cores, however, remain the final holdouts. They continue their own separate dance, orbiting each other in a tightening spiral, their supermassive black holes waiting patiently at the center of it all. This prolonged orbital waltz sets the stage for the most dramatic act still to come, a final union that will reshape the cosmos. This sudden burst of star birth is so intense it has its own name, a starburst. It is the universe's most spectacular fireworks display, a brilliant and furious answer to the galactic collision. The trigger lies in those colossal clouds of gas, the giant molecular clouds that drifted peacefully for eons. When two galaxies intertwine, these clouds do not drift past each other. They slam together at phenomenal speeds. The resulting shock waves act like an invisible hammer, crushing the gas to densities it has never known. Within these compressed, chaotic pockets, gravity finally wins a battle that was once a stalemate. The force pulling the gas inward becomes too powerful to resist, and entire sections of a cloud collapse in on themselves. Each collapse is the seed of a new star, and in a starburst, this happens millions of times over. The galaxy is suddenly filled with the ignition of countless new suns. Many of these newborn stars are truly monstrous, forming as massive, hot, and brilliantly blue giants. They burn through their nuclear fuel in just a few million years, a fleeting moment in cosmic time. Their short, violent lives end in spectacular supernova explosions, but while they shine, they light up the merging galaxies with an ethereal blue glow that can outshine all the older stars combined. We see this phenomenon playing out in systems like the Antennae galaxies, where vast, glowing regions of pink and blue mark these stellar nurseries. These are not gentle birthing grounds, but frantic, chaotic factories, forging new suns at a breakneck pace. And within that furious activity, something even more profound is being seeded. The intense heat and pressure inside these clouds, and the eventual death of the massive stars, forge heavy elements and scatter them into the surrounding space. This enriched gas and dust becomes the raw material for future planets, and perhaps for life itself. The starburst is not just a light show, It is the universe laying the foundation for entirely new worlds amidst the glorious chaos. This frantic starburst activity does more than just light up the cosmos. It builds structures of immense scale and durability in the most intensely active regions where the colliding gas clouds are at their thickest. Something extraordinary coalesces. These are superstar clusters, celestial cities of stars born from the same cataclysmic event. A single one of these clusters can contain hundreds of thousands of stars, all bound together by their mutual gravity, all shining with the brilliant blue light of youth. They are not scattered randomly, but packed into a region of space that might be only a few dozen light years across. To put that density into perspective, if you placed a similar cluster in our own galactic neighborhood, the night sky would be filled with stars as bright as Venus, creating an eternal, dazzling twilight. These superstar clusters are not just temporary features. Astronomers believe they are the infant versions of the ancient globular clusters we see orbiting mature galaxies like our own. Those old, dense balls of stars are some of the most ancient objects in the universe, and for a long time their origin was a mystery. Now we see their violent birthplaces in the fiery hearts of colliding galaxies. The extreme pressure of the galactic collision is the key, forcing unimaginable amounts of gas and dust together into a tightly packed, self-gravitating bundle. This single event creates a stellar structure that can survive for billions of years, a permanent monument to the chaotic merger that gave it life. Long after the initial blue giants have exploded and the starburst has faded, these clusters remain, enduring legacies of the collision scattered throughout the new galaxy. At the very heart of this cosmic construction site, the final bosses are waiting. Nearly every large galaxy, including our own Milky Way, has a supermassive black hole at its center. These are not the dark, quiet voids you might imagine. During a galactic merger, they are stirred from their slumber. As the galactic cores complete their long dance, these monstrous entities are dragged by gravity toward the center of the newly forming galaxy. They begin their own slow, inexorable spiral inward, and on their way they are presented with a feast. The chaotic collision funnels unimaginable amounts of gas and dust directly toward them. As this material spirals into the black holes at near light speeds, it doesn't just vanish. It forms a superheated, brightly glowing disk of plasma around each one. This transforms them into what astronomers call an active galactic nucleus, or AN. A single AGN can become so brilliantly luminous that it outshines every single star in its entire host galaxy. This is a beacon of raw power visible across the universe, but this brilliance comes with a cost. The intense radiation and powerful jets of particles blasting from the active black holes pour tremendous energy into the surrounding galaxy. This energy heats up the remaining reservoirs of cold gas, the very fuel needed to form new stars. It's like a cosmic wind blowing out the candles of star birth, potentially quenching the starburst and putting a halt to the galaxy's frantic period of creation. This is the central paradox, where the same event that triggers a firestorm of new suns also carries the seeds of its own end. Yet, the black holes themselves are not done. Their inward spiral continues, tightening over millions of years until they are close enough to feel each other's overwhelming gravity. Their final collision is one of the most cataclysmic events possible in the universe. When two supermassive black holes finally merge, they do not do so quietly. They create ripples in the very fabric of spacetime itself. These are gravitational waves predicted by Einstein over a century ago, and we can now detect them with advanced observatories like LIGO and Virgo. The merger sends a thunderclap of these waves across the cosmos, a permanent signature of the violent union that forged a new galactic core. This final merger of the black holes marks the closing chapter of the collision, but it is the fate of the galaxy itself that reveals the ultimate outcome. The elegant spiral structures we began with are gone, their delicate arms stretched and shredded by gravitational tides. The orderly rotation, where stars moved in a synchronized disk like horses on a carousel, has been completely randomized. Stars are now flung onto chaotic, three-dimensional orbits, buzzing around the galactic center in every direction like a swarm of enraged bees. The result is no longer a flat, spinning pinwheel. The galaxy puffs up into a vast, three-dimensional ellipsoid, a shape resembling a giant cosmic football. This is the birth of an elliptical galaxy. This transformation is not a rare event. It is a primary reason our universe contains such a variety of galactic shapes. The beautiful spiral galaxies are often the precursors, the raw material for these larger, more amorphous structures built through violent mergers. We see this story written across the sky. Our own Milky Way and its great neighbor, the Andromeda Galaxy, are both majestic spirals today, but they are on an inescapable collision course. In about 4.5 billion years, they will begin their long dance, a process that will ultimately destroy their iconic shapes. The two spirals will merge, their stars scattered into a new, random configuration, to form a single, giant elliptical galaxy that astronomers have nicknamed Andromeda. The very identity of our galactic home will be erased, not by destruction, but by a chaotic rebirth into an entirely new form. But what does this galactic chaos mean for the worlds already in existence? While stars almost never collide, their planetary families face a far less certain future. The gravitational stability that allowed planets to form and orbit peacefully for billions of years is suddenly shattered. As a star is whipped onto a new, erratic path by the galactic tug-of-war, its planets are forced along for the ride. The delicate gravitational balance holding a solar system together can be violently upset. A gas giant like Jupiter could be ripped from its orbit and sent spiraling away into the dark, its family of moons cast adrift. An Earth-like world in the habitable zone might find itself flung completely free of its star, becoming a rogue planet. This would be a death sentence, a world ejected into the permanent, frozen night of interstellar space, its atmosphere slowly freezing out onto the surface over eons. Even if a planet manages to stay bound to its star, its orbit could be drastically altered. A previously circular, stable orbit could be stretched into a long, narrow ellipse. This would subject the world to extreme temperature swings, baking it when close to the star and freezing it when far away, a cycle that would likely sterilize any complex life. The danger does not only come from a changed orbit. Every star is likely surrounded by a vast, distant cloud of icy bodies, a reservoir of comets known as the Oort cloud. In a stable galaxy, these objects remain in the deep freeze, but during a galactic merger, the relentless gravitational perturbations can act like a giant hand, shaking this cloud violently. The result would be a storm of comets sent hailing inward toward the inner planets. For a world like Earth, this would be a catastrophic bombardment, an event far exceeding the asteroid impact that wiped out the dinosaurs. The sky would fill with fire, and the resulting chaos would shatter ecosystems. For any civilization living on such a world, the true threat of a galactic collision would not be a star crashing into their sun, but this slow, gravitational unraveling of the very fabric of their cosmic home. Amidst this gravitational turmoil, a profound creative force is unleashed. The violent compression of gas and dust clouds does far more than ignite new stars. It builds the very cradles for the next generation of worlds. Around many of these newborn suns, the swirling chaos settles into a vast, spinning disk of material. This is a protoplanetary disk, a flat, pancake-like structure where the future of an entire solar system is decided. Within this disk, the universe begins its most delicate work. Microscopic particles of dust, no larger than specks of smoke, float in the void. As they orbit the young star, they gently bump into one another. Instead of bouncing apart, they stick, held by static forces. These tiny clusters grow, becoming pebbles, then rocks, and then boulders. Over thousands of years, these objects, now called planetesimals, act as gravitational seeds. They sweep up more and more material, their size and pull increasing with every orbit. Some will collide and shatter, but others will merge, growing from city-sized bodies into full-fledged planets. This is how a new Earth or a new Jupiter could be born from the ashes of a galactic wreck. The very material for these worlds is enriched by the collision itself. The heavy elements essential for rocky planets like carbon, oxygen, and iron were not created in the Big Bang. They were forged in the nuclear furnaces of earlier stars and scattered across space by supernova explosions. The galactic collision acts as a giant mixer, churning these precious ingredients from both galaxies into the star-forming clouds. When new stars and their disks form from this enriched soup, they contain all the necessary building blocks for complex chemistry. The silicon for rocks, the oxygen for water, and the carbon for organic molecules are all present and available. Within these new protoplanetary disks, the seeds of future oceans, atmospheres, and perhaps even the chemistry for life itself are being sown. From the grandest chaos, the universe patiently assembles the foundations of new worlds, one microscopic grain at a time. Yet another invisible force is at work within this cosmic turmoil, one that guides the chaos with an unseen hand. Throughout the vast spaces between the stars, magnetic fields are woven into the fabric of the galaxy itself. These are not simple bar magnets, but immense, complex structures that thread through the clouds of gas and dust. During a peaceful era, their influence is subtle, but when two galaxies collide, these magnetic fields are caught in the storm. As the colossal gas clouds are sheared apart and violently compressed, the magnetic fields trapped within them are twisted and amplified. Imagine a tangled web of invisible threads being pulled tighter and tighter, their influence growing stronger with every passing moment. This amplified magnetic force begins to exert its own pressure, pushing back against the relentless pull of gravity. In some regions, this magnetic support can be the deciding factor, preventing a gas cloud from collapsing and actually slowing down the frantic pace of star formation. It acts as a cosmic cushion, delaying the birth of new suns. In other areas, the twisted fields act like cosmic highways. They channel and funnel vast rivers of gas, directing this raw material along invisible pathways. This focused flow can pour immense amounts of fuel directly into the waiting maw of a supermassive black hole, supercharging its growth and igniting the brilliant beacon of an active galactic nucleus. This invisible magnetic architecture is the silent director of the construction site, determining where material flows and where it piles up. It adds a profound layer of complexity to the chaotic process, meticulously guiding the distribution of the very gas and dust that will one day coalesce into new solar systems and perhaps new worlds like our own. The galactic collision acts as the universe's ultimate chemical refinery. Within the furious starbursts ignited by the merger, the brief, brilliant lives of massive stars come to a spectacular end. These giants, many times heavier than our own sun, burn through their nuclear fuel in only a few million years. When their cores can no longer support their own immense weight, they collapse and then rebound in a cataclysmic supernova explosion. This violent death is far more than a simple flash of light. It is a cosmic forge where the incredible temperatures and pressures create entirely new elements. The blast scatters these freshly minted atoms back into space, seeding the surrounding gas clouds with oxygen, neon, and magnesium. This enriched material becomes the raw ingredient for the next generation of stars and planets. But the stellar explosions are not the only source of these precious elements. In the densely packed environments of colliding galaxies, another, even more exotic event becomes more likely. The neutron stars left behind by some supernova can be thrown together by the chaotic gravity, spiraling inward and merging in an event known as a kilonova. Such a collision is a true alchemical wonder, producing staggering amounts of gold, platinum, and other heavy elements in a single, radiant burst. In that one moment, a neutron-star merger can create more gold than the mass of our entire planet. This newly enriched gas, now laced with a rich variety of elements from both supernova and neutron-star mergers, is then swept up by the ongoing turbulence. It gets mixed into the vast clouds that will one day collapse to form new solar systems. This process fundamentally changes what can be built. A star system born from this enriched soup has a much higher likelihood of forming rocky, terrestrial planets like our own Earth. The presence of silicon and iron allows for a solid, metallic core. Oxygen can combine with hydrogen to form water. Carbon provides the backbone for the complex organic molecules that are the precursors to life. Without these heavy elements forged in the depths of stars and scattered by galactic collisions, our world would simply not exist. The very atoms that make up the ground beneath your feet and the air you breathe were likely created in such a cataclysmic event billions of years ago, a permanent legacy written into the chemistry of our planet. These vast tidal tails do more than just form new stars. In their most spectacular displays, they give birth to entirely new galaxies. The immense rivers of gas and dust pulled out during the collision contain so much material that they can collapse under their own collective gravity. This collapse is not just about forming individual stars, but about creating a whole new self-contained system, a tidal dwarf galaxy. Imagine a city being built not from raw materials delivered to an empty lot, but from the salvaged wreckage of two other, larger cities that collided. That is the origin story of these unique cosmic objects. They are not primordial entities from the dawn of time. They are second-generation galaxies, forged directly from the debris of a violent merger. This makes their composition fundamentally different from the galaxies we typically observe. A normal galaxy, like our Milky Way, is embedded within and dominated by an immense halo of dark matter. This invisible scaffold governs its rotation and holds it together, but a tidal dwarf galaxy forms from the visible, tangible stuff that was stripped away, the gas and the stars. As a result, these newborn galaxies are made almost entirely of normal matter, the kind of matter that makes up you, me, and everything we can see. They are cosmic anomalies, islands of familiar substance in a sea dominated by the unseen. For astronomers, these objects are like natural laboratories. They provide a rare opportunity to study how a galaxy forms and evolves without the overwhelming influence of dark matter dictating its every move. We can watch the pure physics of gas and stars playing out, free from the complication of an invisible partner. This reveals a profound truth about the universe. Galaxies are not only born from the gentle density fluctuations of the early cosmos. They can also be spontaneously created from the chaos and wreckage of titanic collisions, proving that the universe's creative engine is more versatile and more violent than we ever imagined. The violent dance of a galactic merger may end, but its story is permanently etched into the heavens. Long after the new elliptical galaxy has settled into its calm, football-like shape, the evidence of its chaotic birth remains visible in its outermost reaches. The immense gravitational tides that stretched the original galaxies did not simply relax. they flung billions of stars out into the vast, dark halo surrounding the new galactic core. These stars did not scatter randomly. Instead, they were arranged into elegant, faint ribbons that wrap around the galaxy in great looping orbits. These are stellar streams, the cosmic equivalent of a fossil record. They are the lingering ghosts of the galaxies that once were, orbiting in silence for billions of years after the collision's final act. For astronomers, these streams are more than just celestial debris. They are a treasure map to the past. By carefully mapping the positions, motions, and even the chemical compositions of the stars within these streams, scientists can perform a kind of galactic forensics. They can trace the streams backward in time, computationally rewinding the cosmic clock to identify the original galaxies that merged. They can determine their approximate sizes, their paths of approach, and even when the long-ago collision occurred. This turns the static night sky into a dynamic history book, with each faint stream telling the story of a lost world island. We do not need to look to distant galaxies to see this phenomenon in action. Our own Milky Way, a seemingly pristine spiral, is in fact a cosmic cannibal. Data from the Gaia Space Observatory has meticulously charted the motions of over 1 billion stars, and within that vast dataset, the ghosts of past meals are clearly visible. Multiple stellar streams weave through our galaxy's halo, the shredded remains of smaller dwarf galaxies that ventured too close and were torn apart by the Milky Way's gravity over the eons. These are not the results of a major collision, but of a slow, steady assimilation that has built our galaxy into what it is today. Every large galaxy we see is likely a composite, a silent museum of its own violent history, with the evidence written in starlight across the dark canvas of its halo. This brilliant ignition of a quasar marks the climax of the merger's violence. The chaotic dance of two galaxies funnels an unimaginable feast toward their central supermassive black holes. Vast rivers of gas stripped from their peaceful orbits are channeled directly into the gravitational wells at the galaxy's core. As this material spirals inward, it does not fall straight in. Conservation of angular momentum forces it to flatten into a furious, spinning disk, a structure known as an accretion disk. The gas in this disk is compressed and heated through immense friction and gravitational forces, reaching temperatures of millions of degrees. It glows with a ferocious intensity, emitting light across the entire electromagnetic spectrum, from X-rays to radio waves. This is the birth of a quasar, a beacon so luminous it can outshine 1 trillion suns, making it one of the brightest single objects in the entire cosmos. For a relatively brief period, perhaps a few tens of millions of years, this central engine becomes the dominant force in the newborn galaxy. Its radiation is so powerful that it exerts influence far beyond the galactic core. The intense light and heat from the quasar create tremendous outward pressure, driving colossal winds of superheated gas that blast through the galaxy. These outflows scour the interstellar medium, violently pushing the remaining star-forming gas away and heating it to temperatures where it can no longer easily collapse. In this way, the quasar acts as a cosmic regulator, the very same process that feeds the black hole and creates such a brilliant display also systematically shuts down the galaxy's star-forming factories. It is a spectacular act of self-sabotage, where the galaxy's central heart temporarily quenches the stellar birth happening across its own body, bringing the frenzied starburst to an end and steering the galaxy toward its final, quiet form. This interstellar medium is the galaxy's lifeblood, a diffuse ocean of gas and dust from which everything is born. A galactic collision churns this ocean into a raging storm. Shockwaves, born from the supersonic slam of gas clouds, race through the void. They do not hit evenly. Some regions are hammered by these waves, the gas crushed to such incredible densities that it ignites into the brilliant blue fires of new stars. Other areas are stretched thin, rarefied into near nothingness by the same cosmic forces. This is a frantic, all-consuming consumption of the galaxy's primary resource. The very gas that took billions of years to accumulate is being rapidly converted into stellar fuel. But the galaxy is not just building, it is also bleeding. The furious pace of star birth creates an equally furious pace of star death. The most massive of these new suns live fast and die young, exploding as supernova within a few million years. Each explosion sends another powerful shockwave rippling outward, and together they generate a relentless gale, a supernova wind that can blow vast quantities of gas clear out of the galaxy forever. This is compounded by the immense energy pouring from the central quasar, its radiation pushing against the remaining gas with the force of 1 trillion suns. This 1-2 punch of stellar and quasar feedback can effectively sterilize the galaxy. The reservoirs of cold, dense gas, the raw material for future generations of stars, are either used up in a single burst of creation or ejected into the void. The result is a celestial retirement. The galaxy, once a vibrant blue factory of new suns, slowly fades to a dull red. Its remaining stars age peacefully, their population dominated by long-lived, cooler red giants. Without fresh gas to spark new starbirth, the galaxy becomes what astronomers call red and dead. It is a cosmic graveyard, beautiful and quiet, its long-term growth cycle brought to a definitive close by the very violence that once gave it such brilliant life. Our window into these cosmic events comes not from a single, fleeting observation, but from the power of prediction. Since a galactic collision unfolds over a span far longer than human history, we cannot simply watch one happen. Instead, we reconstruct the entire process inside the memory of supercomputers. These are not simple animations, but incredibly sophisticated virtual universes built upon the known laws of physics. They are known as n-body and hydrodynamical simulations. The n-body component calculates the gravitational dance between billions of individual stars, tracing their intricate paths as they are pulled by visible matter and the vast, unseen halos of dark matter. Simultaneously, the hydrodynamical part of the simulation models the behavior of the gas. It captures how these colossal clouds collide, how they are compressed by shock waves, and how they ultimately collapse to form new stars. These models also include the crucial feedback from those stars, the supernova explosions, and the radiation from black holes that heat and disperse the gas, regulating the very process of creation. This virtual laboratory allows us to perform an experiment that would otherwise be impossible. We can rewind time to see what two progenitor galaxies looked like before they met. We can fast forward through hundreds of millions of years in a matter of hours, watching the entire violent ballet unfold before our eyes. We can run the same collision over and over, changing a single variable to see how it alters the final outcome. Pioneering projects like Illustris TNG and EAGLE have been instrumental in this cosmic forensics. They have shown us with stunning clarity how the gravitational tides from a merger can stretch a majestic spiral into a formless elliptical galaxy. They have revealed the precise conditions that funnel gas toward the center, igniting the brilliant starbursts and feeding the supermassive black holes until they blaze as quasars. Every time our telescopes capture a snapshot of a galactic collision in progress, like the famous Antennae galaxies, we can compare that single frame to our dynamic simulations. When the virtual universe in the computer matches the real one we see through the lens, we know our understanding of the cosmos is on the right track. These digital realms are our time machines, transforming a silent, static sky into a vibrant story of creation and change. These cosmic collisions are not just theoretical spectacles unfolding in computer simulations. We can see them happening right now in the depths of space. A prime example is the Antennae galaxies, a pair of intertwined spirals located 45 million light-years away. This is the closest and youngest example we have of two large galaxies in the violent act of merging. When we point the Hubble Space Telescope toward them, the view is breathtaking. We do not see two neat, orderly pinwheels. Instead, we see a cosmic tapestry of chaos with dark, tangled dust lanes weaving through a blaze of stellar light. The most striking features are the vast, sweeping arcs that curve away from the central chaos, the tidal tails that give the galaxies their insect-like name. These are the same immense rivers of stars and gas predicted by our simulations, made visible, but the true story of the antennae is written in its colors. Scattered across the wreckage are brilliant, electric blue patches. These are not single stars but superstar clusters, each containing hundreds of thousands of newborn suns, all born from the collision's fury. Interspersed among them are glowing pink regions, vast clouds of hydrogen gas heated to incandescence by the intense ultraviolet radiation from all those massive new stars. This is a starburst in action, a firestorm of creation lighting up the cosmic darkness. The Antennae galaxies offer us a priceless snapshot in time. They are frozen at a specific moment in the multi-hundred-million-year process, caught in the act of their most vigorous star-forming phase. By studying this nearby system, we gain a Rosetta Stone for understanding the violent transformations we see in more distant, fainter mergers. It confirms that the chaotic processes we model in our computers are not just abstract equations. They are the real, beautiful, and violent forces that are, at this very moment, forging new worlds and reshaping the universe. This cosmic dance of creation and destruction is not a distant spectacle. It is the ultimate fate of our own home. Right now, the Milky Way and the Andromeda galaxy are caught in a mutual gravitational embrace, falling toward one another at a breathtaking speed of 110 kilometers every second. Their collision is not a matter of if, but when. In roughly 4.5 billion years, their majestic spiral arms will begin to intertwine, initiating a merger that will unfold over billions more. For any observer on a future Earth, the night sky would become an ever-changing work of art. The Andromeda galaxy, currently a faint, fuzzy smudge, would slowly swell into a brilliant, sprawling disk. As the two galaxies draw closer, their structures would warp and blend until the familiar band of the Milky Way is joined by a second, then merged into a single, chaotic tapestry of light. What will become of our solar system in this upheaval? The vast spaces between stars mean our sun will almost certainly survive the encounter. It will not be destroyed, but it will be evicted. The gravitational chaos will likely fling our entire solar system onto a new, much wider orbit, pushing it far out into the galactic suburbs of the newly formed giant. From this distant vantage point, our aged sun, by then a swollen red giant, would watch as the two galaxies complete their merger. The elegant spirals we know today would be gone, replaced by the amorphous, football-like shape of a new elliptical galaxy, a cosmic entity that astronomers have already named Andromeda. Our star will have witnessed the entire cycle, from the ordered beauty of a spiral to the chaotic violence of a collision, and finally to the quiet, stable retirement of an elliptical giant, a perfect testament to the universe's endless cycles of rebirth. But this cosmic construction site is a brutal and unforgiving place. The protoplanetary disks forming within these chaotic stellar nurseries face dangers their peaceful cousins never know. In a quiet galaxy like our own, a young star and its disk can form in relative isolation, shielded within a calm spiral arm. In the heart of a galactic merger, there is no such peace. These infant solar systems are bathed in an intense, relentless glare. The same massive stars that light up the nebula with their brilliant blue light also emit a torrent of ultraviolet radiation. This invisible energy is a destructive force, acting like a cosmic blowtorch on the delicate gases of a protoplanetary disk. For a young, rocky planet slowly coalescing near its star, this radiation can literally cook its atmosphere away, stripping it layer by layer into the void before it ever has a chance to stabilize. The danger is not only from radiation. The stellar density in these superstar clusters is immense, and close encounters are common. As another star passes nearby, its gravity tugs and distorts the disk. This gravitational perturbation can be catastrophic. It can fling forming protoplanets out of the system entirely, or send them careening into chaotic, unstable orbits that doom any chance of a stable, life-friendly system. The orderly process of planet assembly, a delicate dance of dust and gravity, is constantly being shaken and disrupted by its violent surroundings. Yet within this very chaos lies a paradoxical spark of potential. The same gravitational nudges that can destroy order might also be essential for creating habitable worlds. In a stable, quiet disk, material tends to stay in its lane. Ice and water remain frozen solid in the cold outer reaches, while the inner region is a dry, rocky desert. But when a passing star stirs the pot, it can fling icy comets from the disk's outer fringe inward on a collision course with the young rocky planets. This celestial bombardment, while violent, could be the very event that delivers the oceans to a barren world. The chaos that threatens to tear a young solar system apart might also be the force that seeds it with the water and organic compounds necessary for life to one day emerge. The difference between a sterile rock and a living world may come down to the precise nature of the chaos it was born within. Could a new Earth be born from such a violent beginning? The chaotic crucible of a galactic merger, for all its destruction, creates a unique recipe for habitable worlds. The furious starbursts forge and scatter the essential heavy elements, enriching the cosmic clouds with the very ingredients for rocky planets. When new stars ignite from this enriched material, a significant number will be similar in size and temperature to our own Sun. Around these stable, long-lived stars, the physics of planet formation takes its course. Protoplanetary disks will coalesce, and within them, gravitational accretion will build new terrestrial planets. Many of these worlds will find themselves orbiting within that star's habitable zone, the region where temperatures are just right for liquid water to exist on their surfaces. These would be second-generation planetary systems, their very substance forged in the death throes of massive stars and the turbulent mixing of two galaxies. They begin their lives in a maelstrom, bathed in intense radiation and gravitational upheaval. But the violence is not eternal. Over billions of years, the merger remnant settles into the calm, steady state of an elliptical galaxy. The stellar bombardment ceases, the frantic star birth ends, and a profound quiet descends. In this new, stable environment, a planet born from chaos would finally find peace. It would orbit its star for eons, its molten surface cooling to form a solid crust, its atmosphere stabilizing, and its vast oceans pooling in deep basins. The very elements of life, baked into its core from the beginning, would have the time and the tranquil conditions to combine into ever more complex forms. While the odds are steep, the sheer number of new stars and planets created in a major merger means the statistical probability is real. Across the vastness of the cosmos, galactic collisions may be the universe's most dramatic and effective foundries, not just for stars, but for worlds with the potential to one day stir with life. This violent stellar nursery holds the potential for an even greater cataclysm. The dense, chaotic environments of merging galaxies are perfect for forming the most massive stars imaginable, monsters dozens of times heavier than our Sun. These giants live fast and die young, and their deaths are anything but quiet. When such a star exhausts its nuclear fuel, its core can no longer support its own immense weight. It collapses in on itself in a fraction of a second. Under the perfect conditions, this collapse does not result in a typical supernova. Instead, it triggers the single most powerful explosion known to exist in the modern universe, a long-duration gamma-ray burst. For a few fleeting seconds, this one event can outshine every other star in the entire observable cosmos combined. It is a flash of pure energy so intense it can be detected from billions of light years away. The physics behind such an event is extreme. Astronomers believe a gamma-ray burst is the birth cry of a new black hole, a signal that a stellar core has collapsed past the point of no return. The dying star channels its remaining life force into two narrow, opposing jets of radiation and particles, accelerated to almost the speed of light. If one of those jets happens to be pointed directly at Earth, we see it as a brilliant, terrifying beacon across the ages. This is where the galactic collision becomes a direct catalyst for destruction on an unimaginable scale. The frantic starburst activity in a merger dramatically increases the number of these massive stars being born. More of these stellar monsters mean a higher probability that one will die in just the right way to produce a gamma-ray burst. The large-scale chaos of two galaxies intertwining is therefore directly linked to the most energetic and rare stellar deaths possible. A single such event, focused into a pencil-thin beam, could sterilize entire planetary systems across its path, a stark reminder that the same creative forces that build new worlds also wield the power to scour them clean in an instant. The very atoms that will become future worlds are forged in this galactic tumult. A galaxy's potential for creating planets like our own is not just about starlight and gravity, but about its chemical richness, a property astronomers call metallicity. This is the fraction of a galaxy's mass made up of elements heavier than the primordial hydrogen and helium, everything from the carbon in our cells to the iron in our planet's core. Before a collision, this chemical wealth can be unevenly distributed, with pockets of high and low metallicity scattered like islands across the galactic sea. The merger acts as a cosmic blender on the grandest possible scale. The immense gravitational forces stir the galactic gas with a ferocious intensity, thoroughly mixing these isolated pockets together. The result is a homogenized soup, a well-mixed reservoir of gas where new stars will form from a relatively uniform chemical recipe. This mixing is a game-changer for planet formation. When a star is born from this enriched and blended material, its surrounding protoplanetary disk inherits a rich supply of heavy elements. This directly increases the amount of solid, rocky material available to clump together. A higher metallicity means there is more dust and ice to form planetesimals, the building blocks of planets. It dramatically raises the probability that a star will be surrounded by terrestrial, Earth-like worlds rather than just gaseous giants. But the significance goes far deeper than just providing the bricks and mortar for a planet. This chemical enrichment seeds the disk with the very ingredients for complexity. Elements like carbon, oxygen, nitrogen, and phosphorus are the fundamental components of the complex molecules that are the precursors to life. They form the amino acids, the lipids, and the nucleobases that are essential for biology as we know it. A galactic collision, therefore, does more than just build new solar systems. It systematically raises the chemical potential of an entire galaxy, infusing its future worlds with the elemental diversity needed to one day, perhaps, stir with life. The most dramatic collisions are not the only ones that shape the cosmos. For every titanic clash of spiral giants, there are countless quieter, more lopsided encounters. These are the minor mergers, where a large galaxy like our own slowly consumes a much smaller dwarf galaxy. The scale is different, but the gravitational principles are the same. The immense pull of the larger galaxy stretches the dwarf, pulling it apart over billions of years in an act of galactic cannibalism. The resulting firestorm of Starburst is less intense than a major collision, but it is far from insignificant. These events can spark localized starbursts, lighting up the larger galaxy's outer regions with pockets of new stars. They also have a profound structural impact. The incoming stars from the dwarf galaxy, flung onto new and different orbits, help to puff up and thicken the larger galaxy's disk. Many more are scattered into the vast, sparse halo that surrounds the galactic core, adding to its population of ancient stars. This is not a one-time event in the distant past. It is a continuous, gentle form of galactic growth and maintenance happening all around us. We are living through such an event right now. Our Milky Way is currently in the process of digesting the Sagittarius dwarf spheroidal galaxy. This small companion has orbited our own for billions of years, and with each pass, our galaxy's gravity strips away more of its stars. Data from the Gaia spacecraft has given us a breathtakingly precise view of this ongoing feast. By mapping the motions of over 1 billion stars, Gaia has revealed how the gravitational influence of the Sagittarius dwarf is creating ripples and waves in our galaxy's stellar disk, like a stone dropped into a pond of stars. It is actively stirring up the galactic population, a subtle but constant reminder that even our seemingly stable Milky Way is a dynamic, evolving entity, built from the remains of smaller neighbors it has consumed over the eons. This final outcome hinges on a single, crucial ingredient, the gas. When two gas-rich spiral galaxies, like our own Milky Way and Andromeda, plunge into one another, they possess vast reservoirs of cold, dense hydrogen. This gas is the primary fuel for star formation, and its collision is what ignites the spectacular firestorm. The resulting starburst is so voracious it consumes this fuel in a relatively short cosmic timescale, and the subsequent feedback from supernova and quasars blasts much of the remainder away. The end product is a red and dead elliptical galaxy, a celestial retirement home where star formation has effectively ceased. The creative chaos of the merger ultimately exhausts the very resource that powered it. But imagine a different scenario, a collision between two galaxies that have already lived long lives. These are the gas-poor elliptical galaxies, having likely exhausted their gas in prior mergers or through internal processes. When these stellar systems meet, the result is what astronomers call a dry merger. It is a quiet, almost ghostly affair. With little to no gas left to collide and compress, there is no starburst, no brilliant blue nurseries of new stars. The event is devoid of that creative fire. Instead, the two populations of stars simply mingle, their gravitational fields combining to form a single, larger elliptical galaxy. It is a cosmic consolidation, a stacking of assets without any new construction. This fundamental dichotomy reveals a profound truth. The initial conditions of the galaxies, specifically their gas content, act as a master switch. It dictates whether a merger will be a violent, creative explosion that forges new worlds and then quenches itself, or a quiet, stately union that merely builds a larger stellar city from old parts. The universe's capacity for creation in these events is not infinite. It is dictated by the raw materials available at the start of the dance. The visible light from these cosmic crashes is only a fraction of the story. To truly understand a galactic collision, astronomers must listen to the full symphony of light, from the deep bass of radio waves to the piercing treble of X-rays. Each wavelength across the electromagnetic spectrum reveals a different chapter of the chaotic narrative. When we look at a merging galaxy in ordinary light, we see the brilliant blue star clusters and the dark, obscuring lanes of dust. But what lies behind that dust, hidden from our eyes? This is where the infrared vision of telescopes like Spitzer and the James Webb Space Telescope becomes our superpower. Infrared light slips through the dust like a whisper, allowing us to peer directly into the heart of the most violent stellar nurseries. These observatories show us the true, hidden scale of the starburst, revealing millions of infant stars still wrapped in their dusty cocoons, their formation completely invisible in any other light. Meanwhile, the serene, silent gaze of radio telescopes tells another tale. They are tuned to detect the faint signature of cold hydrogen gas, the primary raw material for building stars. By mapping this atomic fuel, astronomers can trace the immense tidal tails and the vast reservoirs of gas being funneled toward the galactic centers, watching the very logistics of star formation play out on a cosmic scale. And then there are the X-rays, the signature of extreme violence. Observatories like Chandra capture the glow of gas heated to millions of degrees. This superheated plasma is created by the shock waves from countless supernova explosions and by the furious friction within the accretion disks feeding the supermassive black holes. It is a map of the most energetic processes in the entire system. By weaving these different views together, we create a multi-messenger portrait of the collision. We can track how energy flows from the stellar explosions to heat the gas, and how that same gas cools and collapses to form new stars. We see the full, chaotic cycle of creation and destruction, a process that remains largely invisible if we only look with our eyes, proving that the universe's greatest dramas are written in many different kinds of light. This brilliant, chaotic light show is not entirely what it seems. Much of the raw energy unleashed in a galactic merger remains hidden from our eyes. The furious starbursts create an intense flood of ultraviolet and visible light, but this radiant energy does not travel far before it slams into the immense clouds of dust churned up by the collision. These tiny, dark grains, the soot of the universe, absorb the starlight. They do not hold onto that energy for long. The dust particles are heated until they glow, and they re-radiate all that captured power back into space, but they do so in a different form. They shine in the infrared part of the spectrum, a form of light our eyes cannot see, but one that our most advanced telescopes can detect as a gentle, pervasive warmth. This process is happening on a truly cosmic scale. In the early universe, when galaxies were close together and collisions were a common event, the cosmos was filled with these dusty, merging systems. Each one contributed its own faint, infrared whisper to the void. Over billions of years, the collective glow from countless galactic mergers built up into a faint, uniform radiance that permeates all of space. This is the cosmic infrared background, a diffuse light that fills the gaps between every star and galaxy we can see. For cosmologists, this background is not just a ghostly afterglow. It is a fossilized record of the universe's most violent and productive era. By carefully measuring the total intensity of this infrared bath, scientists can perform a kind of cosmic accounting. They can calculate the total amount of star formation that has ever occurred throughout cosmic history. The results are staggering. A significant fraction of all the stars that have ever shone, perhaps as many as half, were not born in the quiet isolation of spiral arms like our own. They were forged in the frantic, dust-shrouded firestorms of colliding galaxies. This means the gentle infrared light that fills the darkness between the stars is a permanent memorial to the universe's most violent creative acts, a silent testament to the chaos that built our cosmic home. The brilliant chaos of the merger does not last forever. Eventually, the storm subsides and the new galaxy enters a phase of profound quiet, a period astronomers call secular evolution. Without the dramatic external trigger of another galaxy, the system is left to its own devices, evolving through slow, internal processes over billions of years. In some cases, if enough gas has settled back into a rotating disk, a central bar structure may form. This bar acts like a cosmic traffic circle, funneling the last reserves of gas inward toward the galactic center, potentially sparking a final, gentle wave of star formation. In rare instances, this process can even regrow faint, ghostly spiral arms within the new disk, a delicate echo of the majestic structures destroyed in the collision. At the galaxy's heart, the supermassive black hole, now merged into a single entity, has consumed the last of its feast. Deprived of fuel, its brilliant accretion disk fades, and the quasar's blinding light winks out. The central engine becomes dormant once more, a silent titan sleeping in the dark. Yet the legacy of the violent merger is permanently etched into the galaxy's character. Its football-like elliptical shape is a direct result of the stellar orbits being randomized during the collision, a form it will retain for the rest of its existence. Its overall stellar population is now overwhelmingly old, dominated by the long-lived red stars that survived the merger and the stars born in its initial firestorm, which have now aged together. And if you could look closely at its vast, dark halo, you would still see the faint, looping stellar streams, the fossilized remains of the two galaxies that once were, forever orbiting in silent testimony. The chaotic birth gives way to an eon of cosmic tranquility, and within this new, stable environment, the countless worlds forged in the turmoil, the planets born from enriched dust and delivered water by chaotic nudges finally find the peace they need. They continue their endless journeys around their stars, their surfaces cooling, their oceans settling, and their chemistries stirring, all under the calm light of an aging sun in a galaxy that has finally found its quiet. This grand cosmic cycle forces a humbling perspective on our own existence. Every atom of your body tells a story of ancient violence and creation. The iron that carries oxygen in your blood was forged in the final moments of a massive star's life, a supernova detonation that likely occurred during a galactic merger billions of years ago. The calcium that strengthens your bones was created in that same stellar furnace and cast into the void. These elements drifted for eons, eventually finding their way into the dense, enriched cloud that collapsed to form our sun and its family of planets. Our solar system did not form in an isolated, pristine corner of the galaxy. It was born from materials that were mixed and distributed by the gravitational chaos of earlier cosmic collisions. We are, in the most literal sense possible, the children of that chaos. Your very existence is a direct consequence of galaxies that collided long before our sun was even a glimmer in the cosmos. This realization shatters the illusion of separation. We are not just living in the universe, we are a functional, conscious part of its ongoing evolution. The same violent processes that tear galaxies apart are the very same forces that built the stage for life to emerge. This connection ties your personal story to the most epic events imaginable, a permanent bond written into the chemistry of every cell. Ultimately, the collision of galaxies reveals a universe that thrives on transformation. This chaotic process is not a story of random destruction, but a deeply creative one. It is the mechanism through which the cosmos renews itself, forging new stars from ancient gas and sculpting new worlds from the enriched debris of stellar explosions. The gravitational dance that spawns immense tidal tails, the brilliant starbursts that illuminate the void, and the quiet assembly of new planetary systems within the turmoil are all chapters in the same epic. They demonstrate that creation and change are fundamental forces, woven into the very fabric of space and time. Our own story is now part of this grand narrative. The future merger of the Milky Way and Andromeda is not an end, but a transition into a new cosmic era. It is a reminder that the universe is in a constant state of becoming, forever remaking itself from the ashes of the old. And within that endless, beautiful chaos, the potential for new worlds and perhaps even new life is always on.